let's continue to take a look at the substitution method for recurrences, and in particular we'll build towards an example on binary search. Before we do that, let's play a guessing game. So we'll play a high-low guessing game. I'm going to think of a number between 1 and 15 inclusive. You have a chance to make up to 4 guesses, and after each guess you make, I'm going to tell you either that your guess is too high, or that your guess is too low, or that you got it and you win $100. So what's your strategy going to be? A simple strategy would just be to guess 1, 2, 3, or maybe 5, 6, 7, or maybe 15, 14, 13, and so on. Anyway, another approach would be to just randomly pick numbers using some sort of a random or pseudo-random number generator. But both of those seem pretty naive. So consider what happens if your first pick is 8. So again, I've thought of a number between 1 and 15. You're going to pick 8. And there are 3 outcomes. I'm either going to tell you that your number is too low. So if I tell you your number is too low, what do you know? What information can you extract from that? So you picked 8, your number is too low. That means that your number is greater than 8, right? And we know that the range is 1 to 15. So at this point, you know that it's between 9 and 15 inclusive. On the other hand, if I told you that your number was too high, you would then know that the number was less than 8. And again, our range is 1 to 15, but now we know that it's less than 8. So now you've essentially limited your choices to 1 to 7. Okay, in either of these two cases, you've basically cut down the number of things you have to consider by half. Okay, by the way, the third option was you guessed my number and you win. Yay. Okay, so we can reformulate this strategy that we just looked at, this idea of picking a middle number to reduce the number of choices in half, into an algorithm. So this algorithm will be based on the low value and the high value. We'll select the middle value, which will be the high plus the low over 2, and we'll go ahead and take the floor of that. So we'll be working with integers, integer division. The guess will be based on that middle value. If the guess is right, great. If it's too low, we can repeat this process over again. So here it's expressed with recursion. And if we were too low, we update what we consider to be our low value. So if the middle value was too low, we'll step 1 step to the right of the middle value plus 1, up to and including the height. On the other hand, if our guess was too high, we'll reduce in our high value. So we know that our high value will be below the middle value, so we'll subtract 1 from the middle value. Okay, let's take a minute and draw kind of a picture of this example, and I think we'll see something familiar. Okay, let's imagine that we've got our guessing game, and we know that it's a number between 1 and 15 inclusive. And we'll make our first guess, and we'll use the approach that we just outlined, and our guess will be 8. Okay, at this point, there are 2 outcomes, 3 outcomes. It's possible the number's correct, or it's possible it's too high, or that it's too low. So let's imagine that 8 is too high. At this point, we know that the maximum that we could get would be 7, so our range is now 1 through 7 inclusive. And of course, if the range is 1 through 7, we would go ahead and pick 4 to be our next guess. And again, 4 could be the correct answer, or we could have our 2 different outcomes. So if 4 is too high, we now know our number is somewhere between 1 and 3, and we would probably guess 2. And again, we've got 2 different outcomes. At this point, if our number is less than 2, it must be 1. And if our number is greater than 2, it must be 3. Going back, if our guess was 4 and we were too low, we now know that our value must be greater than 4, but it must be less than 7. So we would guess 6. And again, 2 outcomes. If it's less than 6, it must be 5. If it's greater than 6, it must be 7. Okay, back to our very first guess. If our first guess was too low, we know that it's going to be greater than 8, so it'll be 9, up to and including 15. And we would guess 12. And again, this is going to break down into 2 different outcomes. It's either less than 12, in which case our maximum value will be 13, and our minimum value will be 9. I'm sorry, our maximum value would be 11, less than 12, that's 11, and our guess would be 10. And again, if it's less than 10, it must be 9. If it's greater than 10, it must be 11. And if instead it were greater than 12, we now know that we're in the range of 13 to 15. We would guess 14. If it's less than 14, it must be 13. If it's greater than 14, it must be 15. Okay, at this point, hopefully you recognize a familiar shape. Based on the overall shape and some of our previous work, you can probably develop some insight into the number of guesses that would be needed for this guessing game to be guaranteed to arrive at the right answer. Okay, now let's talk about the concept of binary search, which is really just an indirect version of the high-low game. So binary search works on a sorted array. So you've got an array that's already sorted by its values. It's important that it be an array and that it have the random access property. The goal is to search and see if a particular value is in the array. If the value is in the array, you return its index. And if it's not in the array, you return a sentinel value. So by sentinel, I mean a special guard value, something that actually wouldn't be a valid indicator that the data is in the array. So for things like this, -1 is a common choice. This is one way to kind of handle errors or special conditions. This is a lot like our previous approach, but there's a subtle change in what a guess means. The guess is a location or an index in the array. And comparisons are the values at that index. So as an example, imagine that we've got an array with indices 0 through 14, and their values at each of those different positions. And again, it's important that the array be sorted. So it's values 1, 2, 3, 5, 8. Notice that they're sorted in ascending order. Okay, so imagine that we want to find a particular value. If I'm curious if the number 29 is in the array, we would go through the binary search process to search for it. So again, we would be using locations, indices as our high and low values, but when we ask the question, is this too high or too low, we would be getting the value at that index. Okay, let's work through a concrete example. So we'll search for the number 8 in the array that we just looked at. So again, there are these two concepts we have to keep straight: the location of data, the index, and the value at that location. So the first thing we'll do is we'll look at location 7, so the midpoint of this array. The value at that location is 27. We're looking for 8, and 8 comes before 27. These are in order, so we can throw away all of the values after the 27 and the corresponding indices as well. So by looking at that single spot, we can already throw away half of our array. Okay, at this point, we've limited our range of consideration to 0 through 6. The midpoint of that is 3. The value at location 3 is 5. And we're looking for 8. 8 comes after 5, so we can throw away everything from the 5 and before it. And now we're looking at indices 4 through 6. Okay, so indices 4 through 6, the midpoint is 5. So we'll look at the value there, which is 13. 8 comes before 13, so we'll throw away the 13 and everything that comes after it in the corresponding indices. And that leaves us with just location 4. So we'll look in location 4, and yay, we found the value that we were looking for. So we had 15 items in our array, but we only had to examine 4 of them to find the value that we happened to be looking for this time. Okay, let's develop a recurrence equation for this and look at using the substitution method on it. Okay, so for our binary searches recurrence equation, let's review the form. We're trying to come up with our T of n function, and what we really need is our relationship between one case and the smaller case, and we also need our constant amount of work, or the amount of work at our current instance. Okay, so the non-recursive work at instance of size n, let's just assume that's a constant again. Remember that it's basically just a simple comparison to compute the midpoint and compare the value at the midpoint with the value we're searching for. Okay, so let's think about the g of n function. So based on the work we've done so far, it looks promising. It looks like it's cutting the work in half. It looks like the smaller subproblems are half the size of the original problem. Okay, so it looks like this is the form of our recurrence. Our T of n is equal to the T of n over 2 plus k. So let's try and let's develop a base case for this. So we'll use a default assumption if problems don't specify anything otherwise. So our default assumption is the base case, the T of 1, is some constant. And we'll generally try and pick something that will simplify our other work in our problems. So you'll examine more examples of this in studio activities. Let's try and use the substitution method to find a solution for our T of n function, find a closed form solution. Okay, let's try and demonstrate a particular closed form and see if it works. So again, given our recurrence equation, let's start off with an assumption that maybe this is a constant time formula, maybe T of n is c. So we have to pick the value of constants that may make this reasonable. So let's go ahead and assume that our k constant from our recurrence is equivalent to c. Then let's think about our base case. So no other base case was given, so let's just assume that the base case T of 1 will be a constant. So if T of 1 is a constant, our formula for T of n when n is equal to 1 would also be a constant, so it holds for the base case. So now let's consider the general case. So we'll substitute in our assumed closed form into a recurrence equation. So we'll take our recurrence equation and we'll substitute in our closed form value. So T of n over 2, well, we've said that T of n is equal to c. T of n over 2 would also be equal to c, so that'll give us a c. And then we still have the original c from our recurrence. So we've got a c plus a c, which is 2c. And that's in contradiction with our closed form, which says that the T of n would be equal to c, but instead it appears to be 2c here. So for any constant c greater than 0, this is obviously incorrect. Okay, so our proof failed. Let's move on. Let's try something else. So we know at this point that it's not constant time. It's not too surprising. So let's take another try at it. Okay, so this time let's assume that maybe it's a linear relationship, c times n. Just like before, we need to think about how we're going to assign the constant from our recurrence equation. We'll assume that it's c again. We also need to think about our base case, so T of 1 we'd expect to be c, and let's see if that works out with our assumed formula here. So we would get c times n, where n is 1, so it'd be c times 1, which is just c, so it holds for the base case, so we're good there. Now let's look at substituting this into our recurrence. So our recurrence, if we substitute in for t of n over 2, the t of n is equal to c of n, so that would be n over 2 times c. And of course we still have our other c here from the recurrence equation. So this total gives us c plus c times n over 2. And we were trying to show that this was this would match up with our closed form equation, c times n. So it's not equal, so our proof failed. Okay, so the proof failed, but there's a little bit more to it. So if we consider what we just found, c times n over 2 plus c, and just factor out the c, so it's c times n over 2 plus 1. If you think carefully about the relationship of that to our original equation, so our c times n, so this is c times something less than n plus 1. So we can demonstrate that our left-hand side is always less than or equal to c times n for values of n that are greater than or equal to 2. Okay, so what that means is we've essentially shown that there is some sort of an upper bound. So we've shown that t of n is in O of n, so that means that we're bounded above by O of n. Now, that may not be a tight bound above. Okay, so in order to prove big theta, we must prove both an upper and a lower bound. And at this point, we've got some claim about what might be an upper bound, but it's not a tight upper bound. Let's try one more try. So this time, let's consider log n. So let's assume that our general solution is some constant times log of n. Okay, so again, we still have to demonstrate that our base case is true. So t of 1 would be c times log base 2 of 1. So the log base 2 of 1 would be 0. So 0 times c would be 0. Oh gosh, so that fails with our goal for our base case of t of 1 being equal to c. So it looks like this formula doesn't work as our general solution. But what if we just move the base case over? What if we think of the base case as occurring at t of 2 instead of t of 1? So then t of 2 would be c times the log base 2 of 2. Log base 2 of 2 is 1, so 1 times c is c. Oh, so that works out okay. If we just change what we consider to be our starting point or our base case, this appears to be okay for the base case. We still have to check the general recurrence. So let's go ahead and try that out. So our inductive hypothesis here is that c times log base 2 of n is our solution, our general solution. Closed. Let's go ahead and substitute that into our recurrence. And this is what we come up with. And we can factor the denominator out inside the log and split it into log base 2 of n minus log base 2 of 2. And we can multiply through by c. The log base 2 of 2, by the way, is nearly 1. So when we multiply through by c, we get c times the log base 2 of n minus c times 1. plus our c, and of course these last two plus and minus c's will end up canceling out. Okay, so it looks like we've demonstrated that if we substitute this in to our recurrence equation, that it demonstrates that it is our general solution. So at this point, we've kind of proven an exact bound. All of these are dealing with an exact solution to t of n. Okay, so as an exercise, use the substitution method and work through our heapify equation, t of n equals t of 2/3 n plus k, and show that it's also logarithmic, and as a hint, consider using log of 3/2 as the base. Okay, quick summary of the substitution method. So a review of some pros and cons. So pro, if we've got any recurrence, if given the right guess, you can prove its correctness by doing an induction proof. Also, you can use separate and upper and lower bounds to try and prove big theta. One of the downsides here is that guessing lower order terms for induction can be difficult, guessing those constants, or if we had something that had a lower order term that was something besides constant, it can be difficult to guess those. Okay, so one of the questions we have now is, can this guesswork be removed? It seems problematic to have to guess the right function and then demonstrate that it's true. And in general, no, the guesswork can't be completely removed from the substitution method. But there are some common cases that can easily be dealt with.